This presentation is part 2 of my video on the Iran nuclear threat. This video is a technical video presenting calculated approximate yields of 2 possible nuclear weapon designs using uranium enriched to only 60% of uranium-235. I summarize the possible yields of the 2 weapon designs and estimate the number of deliverable nuclear weapons, assuming Iran did indeed move their stockpile of approximately 400 kilograms of enriched uranium hexafluoride. I further present the possible yields of these 2 designs for enrichment from 20% HEU to 90% HEU. There are 2 possible designs to consider for enriched uranium weapons. The first is a non-implosion design. This design simply assembles the critical mass mechanically before the chain reaction starts to produce a pre-detonation. An example of this is the gun design used in Little Boy that was dropped on Hiroshima, Japan, on the 6th of August 1945. In Little Boy, a critical mass was assembled by rapidly firing a subcritical mass down a gun barrel to mate with another subcritical mass, as shown in the video on the right. It is important to note that the assembly time for this type of weapon is on the order of half a millisecond. A millisecond is 1,000th of a second. The yield was about 15 kilotons. Because uranium-235 requires times longer than half a millisecond for pre-detonation, this design requires no implosion. Only the 2 masses need be slammed together in the space of half a millisecond. In Little Boy, 4 polonium-beryllium neutron sources were simultaneously triggered by the impact of the 2 subcritical masses to help start the chain reaction. The second design I consider is the implosion design, similar to the Trinity test and Fat Man that was dropped on Nagasaki, Japan on the 9th of August 1945. Trinity and Fat Man use complex explosive lenses to crush a plutonium-239 core to achieve a critical mass. A mechanical design would not work because of the slow assembly time. Spontaneous fission of the plutonium-240 isotope, a contaminant in the plutonium core, would cause pre-detonation and a fizzle of little yield. Assembly time had to be much faster than simple mechanical assembly. It had to be on the order of 1 to 4 microseconds. A microsecond is 1/1,000,000th of a second. Plutonium-239 is produced in nuclear reactors by bombarding uranium-238 with neutrons. Unfortunately, the contaminant plutonium-240 is also produced, requiring the much faster assembly time. Nevertheless, production of plutonium-239 in reactors is much faster than the processes to enrich uranium to HEU levels. However, the explosive lens design is a much more difficult engineering process than enriching uranium. It is important to note that implosion is a much more efficient design for a nuclear weapon and can also be used for highly enriched uranium to generate higher yields than the mechanical design. It is not limited to a plutonium core. It is known that Iran has been conducting research on implosion. Using the methods developed in my technical report, The Basic Physics of Nuclear Fission Weapons, I calculated the possible yields of both designs discussed above My technical report is based on the book The Physics of the Manhattan Project by Bruce Cameron Reed. The mathematics is rather complicated and will not be discussed here. They are explained in detail in my technical report and in Reed's book. In the following graphs, the blue curves are the neutron growth rates in the core versus time, and the red curves are the yields versus time from detonation. Note, the time scales are very small. They are microseconds. The neutron growth rates are shown only to demonstrate that they go to zero because of the rapid expansion of the core due to the extremely high temperatures and pressures. The core rapidly vaporizes and expands to the point that it is no longer a critical mass. Here is an example of the yield from a mechanical assembly design. Keep in mind that Iran's current ballistic missile payload capability is a maximum of about 1,000 kilograms. For comparison, Little Boy had a uranium core of 65.8 kilograms, enriched to only 80% of uranium-235. It had a tungsten carbide tamper and an aluminum pusher totaling 552.5 kilograms. It was 28 inches in diameter and 10 feet long. It weighed 4,400 kilograms. The yield was approximately 15 kilotons. Little Boy was designed in the early days of the Manhattan Project, and implosion had yet to be perfected. In 1952, a second gun design was developed for a nuclear artillery shell, the W9. It used 50 kilograms of 90% HEU. It was much smaller than Little Boy, measuring 55 inches long, 11 inches in diameter, and weighing only 365 kilograms. It had a yield of 15 kilotons. This was possible using a beryllium tamper, which has an extremely large neutron scattering cross-section. It reflects neutrons back into the core to significantly increase the number of fissions to boost the yield. This was recognized during the Manhattan Project. However, beryllium was not readily available during the war. This figure shows a possible gun-type nuclear weapon using 51 kilograms of 60% HEU and a beryllium tamper of 300 kilograms. The diameter of the nuclear warhead is about 27 inches. The length would be similar to the W9. The yield is about 15 kilotons, similar to Little Boy, but in a much smaller package. This design is well within the payload capability of Iran's ballistic missiles. The next slide discusses how they could achieve higher yields with implosion. If Iran develops an implosion design capable of a compression factor of 2.5, similar to that of the Trinity test device and Fat Man, they could achieve a weapon yield of approximately 22 kilotons using a core of only 25 kilograms of 60% HEU and a tungsten carbide tamper of only 200 kilograms. This represents an even smaller payload and is also well within their current missile payload capability. It is important to note that explosive lens designs and core tamper designs have come a long way since 1945. It is now possible to achieve even larger yields with levitated pits or cores, hollow pits, and two-point detonation of non-spherical implosion lenses. These designs are beyond the scope of this presentation, and it is not known how much of this technology Iran has. As previously noted, and Contrary to misinformation by the media and certain government officials, nuclear weapons do not require 90% enrichment of uranium to uranium-235. Remember, Little Boy's uranium core was enriched to only 80%. Here is a graph of possible yields versus enrichment for the gun and implosion designs discussed above. There is no unique enrichment or critical mass for a nuclear weapon. It depends upon the specific designs. There are several critical conclusions that can be drawn about Iran's impending nuclear weapons development. If the IAEA is correct, Iran had 408 kilograms of 60% HEU uranium hexafluoride prior to the Midnight Hammer attacks by Israel and the U.S. on their nuclear weapons facilities. Iran claims that they moved their stockpile of this enriched uranium hexafluoride to other secret sites before the attacks. This is not verified. However, such a stockpile would be sufficient for numerous weapons of significant yield. The uranium hexafluoride must be converted to 60% HEU metallic uranium. The conversion factor is approximately 0.676. This is more than enough for 5 mechanical assembly weapons with an approximate yield of 15 kilotons or 11 implosion weapons with an approximate yield of 22 kilotons. If they accept a lower yield, less HEU and tamper materials are required and even more weapons can be produced. Such an arsenal is indeed sufficient to wipe Israel off the map as promised. World War III would inevitably ensue. Therefore, it is imperative that we and our allies prevent Iran from developing such weapons. From the recent Iran missile attacks on Israel, it is obvious that there is no missile interceptor system capable of intercepting multiple missiles at 100% probability. Interceptor systems can be overwhelmed by including large numbers of dummy missiles in a nuclear missile strike. This is a common strategy in missile attack planning.